Welcome back to The Explainer. Today we're diving straight into episode 12, Bit, where the rig meets the rock.
Okay, let's dive right into this. I really want you to picture the sheer, mind-boggling scale of a modern drilling operation for a second. I mean, we're talking about a 200-foot derrick reaching up into the sky, thousands of horsepower roaring away on the surface, literal miles of heavy steel pipe, and a daily operating cost that runs into the millions of dollars. Millions! But here's the crazy part. All of that massive infrastructure, it all exists for one highly specific reason. Think about that mountain of steel and money on one hand, and then think about a single object, roughly the size of a dinner plate, spinning in absolute pitch blackness at the very bottom of the hole. That's the drill bit. And the harsh, undeniable reality of this business is that if this tiny, dinner plate-sized tool isn't cutting, literally nothing else on that rig matters. The mud pumps, the drawworks, the crew, they're all just a support system for this one single component. This is the exact point where the entire industry meets the rock.
Section 1. Two jobs in one. The function of the drill bit.
So, zooming in from that massive rig scale directly down to the bit itself, let's look at what it actually does. Obviously, it's the cutting or boring element that actually drills the well, but to really understand it, we need to focus on the most common type used in rotary drilling, which is the roller cone bit. Now, a roller cone bit is exactly what it sounds like. It's got three toothed cones that rotate as the main body of the bit turns. But here's the kicker, and this is what usually catches beginners completely off guard. It doesn't just have one job. It actually has two simultaneous jobs. It has to break the rock, sure, but it also has to flush the broken pieces away. Every single bit has these circulating passages built right into it to let drilling fluid blast through. And this is absolutely crucial. Doing the first job of breaking the rock without the second job of flushing it away, it's entirely useless. If you don't clear those cuttings, you just end up regrinding the exact same debris over and over again forever, totally wasting all your energy.
Let's break down the physics actually at play down there because it's honestly a beautifully brutal system. First, the drill collars above the bit push down with this massive, crushing weight, forcing those teeth directly into the solid rock. Then the rotation kicks in. That rotation makes the cones roll, which forces each individual tooth to crush and gouge a chip of rock right out of the formation. Meanwhile, and this is where that flushing action happens, drilling mud jets through specialized nozzles on the bit at literally hundreds of feet per second. We're talking high-velocity fluid that sweeps every single chip off the rock face the exact instant it's cut. Why does that matter? Well, a clean face means the bit gets full cutting depth into fresh rock on the very next rotation. A dirty face means you are wasting millions of dollars of rig time just recrushing rubble, and nobody wants to do that.
Section 2. Matching bit to rock. Application is everything.
Now let's talk about the engineering choices, because you don't just grab any random bit off a shelf and start drilling. Picking the wrong bit for the rock you're in is, without a doubt, the single most expensive mistake you can make in drilling. The bit choice absolutely has to follow the geology, and this brilliantly illustrates exactly how tooth geometry strictly follows rock hardness. For soft rock formations, you're going to want long, widely spaced teeth that can scoop out massive bites of rock without clogging up. But what if you hit hard rock with those long teeth? Yeah, they would simply snap right off. So for hard rock, engineers use short, stubby tungsten carbide inserts packed super tightly together. Oh, and if the rock conditions are just right, we use something called a PDC bit. That stands for polycrystalline diamond compact. A PDC bit has fixed diamond cutters, absolutely no moving bearings, and get this, it can drill 10 times the footage of a standard roller cone. It's such a fascinating piece of tech that will actually give PDC bits their very own explainer down the line.
But going back to our trusty standard roller cone bit, how much force are we really applying here? Well, there's a fundamental rule of thumb that every single driller knows by heart. A roller cone bit requires roughly 3,000 to 5,000 pounds of weight per inch of the bit's diameter. Just let that sink in for a second. Up to 5,000 pounds for every single inch.
Let's actually break down the math on that so we can really grasp the unbelievable forces at play. If you're running a pretty common 12¼ inch bit, that formula means you need somewhere between 37,000 and 61,000 pounds of weight pushing down on the bottom of the hole. But, it's a real tightrope walk. You have to find this Goldilocks zone. If you're underweight, the teeth just won't penetrate. You end up just polishing the rock instead of cutting it, which basically destroys the bit. But if you're overweight, that immense pressure simply crushes the internal bearings of the cones to pieces. You have to get it just right.
Section 3. The pencil sharpener analogy. So what exactly happens when things start to slow down? To really demystify the fluid dynamics and downhole hydraulics of this whole system, I want to use an analogy that perfectly explains what most people get completely wrong about drilling. Think about a simple manual pencil sharpener. When a pencil sharpener stops working well, it almost never fails because the blade suddenly went blunt. It fails because the wood shavings pack up inside the little mechanism. The blade is still sharp, right? But it literally cannot reach fresh wood. Drill bits are completely identical in this way. The most common cause of slow drilling isn't a dull bit, it's a dirty hole. The rock shavings pack up, the teeth can't reach fresh rock, and the cutting just grinds to a halt. This is exactly why hydraulics, nozzle sizing, and fluid flow rates get just as much engineering attention as the heavy steel teeth do.
So I want to challenge your instincts directly here for a moment. Imagine you're the driller. Your rate of penetration, basically the speed you're cutting through the earth, is suddenly dropping off. Your instinct, and honestly the instinct of almost anyone, is to push harder, right? Do you reach for the console and just add more weight to the bit?
The answer is a hard no. Adding more weight is almost never the first answer down hole. If your bit is balled up with sticky clay, or the hole just isn't being cleaned of cuttings efficiently, adding more weight is actually going to make the problem so much worse. You'll just pack that sticky cutting structure even tighter into the rock, you'll drill even slower, and you will absolutely wreck those delicate internal bearings. Slower drilling does not equal a need for more weight. You absolutely must diagnose your hydraulics first. You've got to check your flow rate and your torque before you ever even think about reaching for more weight.
Section 4. The nightmare scenario.
Now, what happens if a driller just ignores these limits? What happens if they push a worn roller cone bit just a little too far, maybe to try and save the time of pulling all that pipe out of the hole to change it? Well, that brings us to a reality that has a name that literally makes drillers shiver: a lost cone. If you push a worn bit too long, the journal bearing seizes up, the shear rotational force snaps the cone right off the bit body, and you have just left a massive lump of jagged, hardened steel at the very bottom of the well bore. And guess what? You cannot drill through it. This absolute nightmare is called a fishing job. You now have to trip all your pipe out, run highly specialized fishing tools down there to try and grab it, and you will likely lose days of expensive rig time. In the worst-case scenario, you might even have to sidetrack the entire $1-million well, abandoning that section completely. It's a disaster.
And that beautifully explains our core takeaway for today. Because the stakes of a fishing job are just so astronomically high, bits are pulled out of the hole on a strict mathematical plan. They are never ever run until they die. It is always cheaper to spend 12 hours pulling a slightly worn bit out of the hole than to spend 2 miserable weeks trying to fish a broken cone out of the dark. That entire multi-million-dollar operation we talked about, it all dances to the tune of this one small disposable tool.
So, I'm going to leave you with this thought. The next time you see a used drill bit sitting on a pipe rack somewhere, don't just see a random chunk of metal. Look closely at the wear on the teeth. Look at the play and the bearings. What story is that specific piece of steel telling you about the dark, violent, incredibly high-pressure world 2 miles beneath our feet? It's basically the ultimate physical evidence of a place we can never visit ourselves. Thanks so much for joining me on this explainer. Keep asking those great questions, and I'll catch you on the next one.